Hey everyone, so I'm Jeff. I work at Facebook. I work on our JavaScript infrastructure team. And specifically our team is kind of responsible for measuring and keeping track of the ecosystem of writing JavaScript at Facebook, which is becoming surprisingly popular, especially these days. So I want to talk to you about a couple of milestones that we've had in terms of things that have made it possible for us to scale up writing JavaScript at Facebook. And so I'm just going to dive right into that. So at Facebook, we have this huge code base, as you can see there. And it's really easy for people to bump into each other or writing code. Somebody changes something, and that breaks somebody else's code in an unexpected way and that sort of thing. So the first question when we sat down and started trying to identify some of these issues that we were having as more and more people started writing JavaScript was how can we help make this easier, make it more pleasant experience for people to change code and that sort of thing. So we start with how do we design complicated stuff? How do people actually naturally do this? And historically, well, let me back up for a second. So typically, at least at Facebook, what we do is we start with this high-level big idea in our head, this gray box. And it does all these crazy awesome things, and we know them all, and we can keep them all in our head because it's just a high-level idea. We haven't dived into the minutia and all the details and that sort of thing yet. It's only until we start coding it and breaking it down into smaller pieces, these little chunks of code, that we actually start realizing all the extreme amounts of things that this application or feature or new thing is going to do. And in those cases, we begin to sort of work through these piece by piece to make sort of iterative progress. It's just not reasonable for us to put the whole thing into our head. So we break it down into small chunks of code and we write them and put them together. So historically in JavaScript, we've had scripts to do this, and we would, you write your little chunk of code in one script, and another chunk of code in another one, put it in a browser, they come together, and they work together. So I want to illustrate kind of a contrived but completely plausible example scenario where you go through and you write some code in scripts and you run into some problems with scripts in general. So say we want to personalize our application. We want it to say hello, Jeff, or whatever your name is. And to do that, we want the user to be able to log in through Facebook. So we go and we write a chunk of code like this. And this is just a function that takes some information, has the user log in, comes back with their first and last name, and now we use that in our application, right? Code itself doesn't matter too much. Just the point here is we're building this little chunk of code. So we load it up in our browser after we write it, like in our little dev box, and we test it, and we log in, and it says, hello, Jeff, everything works, so we ship it. So everything's good to go. 3 months later, we decide we want to add support for Twitter as well, right? Some people want to log through Twitter. So we build another chunk of code, and it's almost the same thing as what we just did. We just go and build another function, except this time it calls the Twitter API instead of the Facebook API and comes back with the first name and last name, yada, yada, yada. Same testing plan as well, right? We load it up in our sandbox. We try it. We log in through Twitter, and it says, hello, Jeff. So we ship it, and at that point, we get all of these user emails asking why we took away Facebook login. But we didn't actually take away Facebook login. What we did was we just added support for Twitter. So we have no idea what they're talking about. We start digging, and we realize Facebook login is actually broken, so that's kind of what they were trying to say. Sometimes people don't articulate the problem very well. Well, it turns out, if you look close, we just put 2 scripts in the page, and they both have the same function name. So they've clobbered each other. So historically in JavaScript, you write things in scripts. You write these little red chunks of code in scripts. But these scripts come together, and they share scope. And these scopes, sharing scope like that allows you to bump into each other very easily. And again, when you're writing code like this, we were in the trench of things with writing the Twitter integration. We weren't thinking about the fact that we had another function somewhere in the code base named the same thing. And so there's just no way that we could have actually reasonably have expected ourselves to predict this problem. So clearly this is a fail. We quickly realized that we need a model system, as most of you probably already aware. Model systems are pretty important. Specifically, we went on a search for a model system. We wanted 2 things out of it. The first thing we want, this is really small. The first thing we wanted was whenever we write a module, we want it to be local by default. This very specific scenario outlined here would have been solved if we didn't have to think about the fact that we're clobbering everything when we write code. So we want local by default in our module system. And the other thing that we want is we want to be very explicit when we indicate our imports and exports. Right? We want to explicitly say how all of our little chunks of code and pieces talk to each other. And the reason that's important is because I get to say, when I write the code, who I want that getUserObject function from. It's very important for us to be able to understand that when we're expressing our intent in code. So the first milestone that we had at Facebook, probably 3 or 4 years ago, was just to build a freaking module system. It's really useful. After that, we realized that at this point, we can start focusing on more stuff where people are writing more and more modules. So we began to build a unit testing system for JavaScript. And specifically, what we have today is called Jest. We've open sourced it a few months ago. And there are 3 basic high-level things that we wanted out of our JavaScript testing system that gave us the ability to continue scaling and build on top of that module system. First of all of those tests run in parallel. So that's important, not just from a speed perspective, right? You want that quick feedback loop. But it's also helpful because it ensures that our tests kind of like don't affect each other, right? They're all off running in a different process. They can't possibly accidentally, one test sets something up and another one does something else, and that's bad. So all tests in Jest run in parallel by default. So that was one of our tenets. The next one, and I'm going to talk about this a little later in my talk, but the next one is that we support auto-mocking in Jest. So this is actually a really unique feature to Jest. If you haven't looked at it, basically what auto-mocking does, typically when you go off and write a unit test in pretty much anywhere, you need to start thinking about how you want to deal with isolation. And so what you do to deal with isolation is you go off and you do one of 2 things. You either build a manual mock for all of the dependencies of the code that you're testing, and that's pretty tedious, right? You have to go off and kind of look at the API and mimic it. Or more realistically, in your test, you have a bunch of boilerplate to kind of build up and do the same thing, but you have a library that helps you build a mock. And so you go off and you build your mock in your test, and there's all this boilerplate. And about half of your test winds up kind of being boilerplate for expressing how you want to isolate your test. Jest has some built-in facilities to do this automatically and make it default to that specifically. So when you're testing a module, it's going to automatically help you isolate. But I'll go into that more in a second. But the third thing that we wanted from Jest is we wanted really clear feedback when a test fails. So if you run a test and it gives you a failure message, it's really important that that failure message is pretty actionable. So if you look at a failure message like this, you see that the API library failed. And this is strictly better than just pushing stuff to users and kind of frustrating them and pissing them off. You actually catch the problem before you push to production. But it's still not good enough. We wanted Jest to encourage things that are better than this. So rather than saying API library failed, where I, as a developer, have to go search my entire application, looking through probably API stuff to figure out what went wrong, Jest encourages you to write things in a more structured way, such that the error message you get when a test fails tells you a lot of context about why that test failed. So this was really important for us because it means that when this test fails, I understand that the problem starts at the Twitter API module. Specifically, it's the getUserObject function. And the problem that we observed in this test was that the callback is never called. So I don't have to spend time trying to figure out what the problem is. This gives me a really good starting point. It narrows that problem space of searching through my app to find the problem. So we use Jasmine in Jest, and Jasmine really helps with doing things like this, especially because we started by sort of adding a bunch of tests to the code base that kind of encourage you to, like, the top level test suite is the name of the module, and the next one's the name of the API, and then your test specs kind of describe it. So you get this really nice sort of feature. And it kind of becomes intuitive, and that's the important aspect, right? You want people to do things that are intuitive to them, because that's what they'll do more often, that work out really well in the long run. So the last aspect of Jest that really helped us move quickly is the automatic mocking feature I mentioned earlier. So we realized that if Jest, our test system, understood that our application is being built as a function of a lot of modules, we can use that information while we're running tests and while we're writing tests to be more smart about the things we're doing. So Jest understands our module system. It understands that these modules depend on each other in certain ways. And specifically, it understands how they depend on each other. So Jest is able to actually go in and understand when this module, all of the imports and exports from a module. And that's helpful because whenever you're testing some module, let's say this one, Jest can, all you have to do is tell Jest, I'm testing this module, nothing else. Jest will then look at all of the other modules that surround it, that connect with it, that are imported and exported, that are imported by it. And it will automatically generate mocks for you. So it looks at the exports of those modules and says, oh, you're exporting a function and a constant and a thing and a here. And without you telling it to do anything, it's going to give that module a fake version. It's going to give the module under test a fake version of its dependencies. So this is really powerful because, again, and I keep saying by default because that's kind of the point I want to stress here. By default, you start with isolation. And as you need to reduce isolation, you explicitly tell Jest what you don't want isolated. You can expand this box a little bit if you don't want that module mocked, but you do want this one, and so forth and so on. But you start from mocking everything. So when that test fails, it's very obvious from the error message and from the fact that we trust that Jest is doing this auto mocking and it's keeping us within the bounds of this white box. All we have to do is search inside that module because we know the problem must exist either within that module or test. So again, we've narrowed that search space. So I've breezed through this talk. But basically, the key points here are we started with modules. We built out this module system at Facebook, and it helped us with some implicit aspects. We moved on to testing, which built on top of our module features and stuff that we built at Facebook, modules that we built at Facebook. And both of these things have clearly paid off really well for us. We've observed our code base going up to thousands of modules and tens of thousands of tests. We don't have actually our JavaScript errors have gone down significantly since we've done this. But the one thing that it's become pretty clear is that unit testing really can kind of only get you so far. Unit testing is all about exercising your code. It's about enumerating all of the test cases that you can possibly imagine and making sure that you have as much test coverage as possible. But this is kind of a pipe dream in terms of getting 100% there. And even if you do, sometimes you wind up writing too much tests, and so that kind of affects your feedback loop because you're running tests you don't need. And sometimes you don't write enough tests because you didn't imagine some scenario where these two modules might actually interact with each other or something along those lines. So I'm going to invite Vic up to kind of talk about another tool that we've been working on to kind of help fill in some of the gaps there. And this is kind of fucking cool. Vic is going to show you some of the stuff we've been working on for the past quite a bit of time. So, Vic. Thanks.
Thanks, Jeff. Hey, everybody. My name is Avik Chaudhary. I work on languages and tools at Facebook. And I'm going to talk about some exciting stuff we've been doing at Facebook around JavaScript development for the past year or so. So Facebook loves JavaScript. At Facebook, we write a lot of JavaScript. Why? Because it's awesomely good at the things we use it to do. So it's fast. Developing in it has an immediate feel that fosters creativity and inspiration. It's expressive. You can write quick prototype code in it, but you can also use sophisticated features like functional programming and reflection to build powerful abstractions and frameworks. And it runs everywhere. So once you write your code, it has universal reach. So all of this makes JavaScript really a great language to build rich experiences in. So yeah, Facebook loves JavaScript, but relation status is complicated. Why is it complicated? Well, it turns out that JavaScript is kind of underpowered in areas that really start to hurt as your code base grows. And our code base is really huge. Like how huge, we can't give you a number, but imagine a really big number in your head and multiply it by 10. That huge, right? So what's missing from JavaScript is the ability and all the stuff you need to program in the large. That's what's missing. So we have some experience with this problem. At some point, most of our server-side code was in PHP, and now most of it has been converted to Hack, a programming language that Facebook built just by adding a layer of static typing onto PHP. And this simple idea turned out to be a really great idea. It helped us a lot. So this idea is really powerful. Types form the basis of code intelligence. And once you have code intelligence, you can build tools that help you manage programming in the large. So we want to add types to our JavaScript as well. But wait, we can't just throw any other type system onto JavaScript. That would be pretty naive. First, we want to keep the feel of JavaScript development completely untouched. So there cannot be any compile time delays. All right? So this is pretty rad. On the one hand, we want type checking, but on the other hand, we want feedback to be instant, even on a huge code base. Second, we have to type check JavaScript as it is written at Facebook as well as elsewhere. Now, this is a very subtle point. If you think about it, it's pretty tempting to cut down JavaScript into an easier to tame subset and kind of make a type system for it, basically reducing it to yet another boring language. We don't want to do that. Really, that would make things easier for us, but that would force our developers into a very difficult dilemma. It would tell us basically that remain in the recommended limits, like stay within the limits, code in this recommended style. If you don't, you're completely on your own. And that sucks. For our tools to be useful day to day, we have to understand all of JavaScript, especially the parts of JavaScript that give it so much expressive power. Some of those are kind of hard, but there's not really any choice, right? So our developers at Facebook who write JavaScript are interested in getting shit done. They would not tolerate anything that takes away their freedom of expression. And get this, not even if it was made by us, by Facebook, right? They're free to pull off anything off the shelf and use it if it's better than what we build. All right, so to summarize, we want type checking for JavaScript, yet we have these two non-negotiable constraints. One is do not slow developers down. Two, don't curtail their freedom. So was there anything out there that we could use? Unfortunately, no. We took a good look at TypeScript, as well as a bunch of other type systems for JavaScript as well as related systems. There has been a lot of work in this area. There are lots of good ideas. Unfortunately, none of these type systems could fit all of our use cases, and they did not scale as well as we wanted them to. So what we realized is that what we need is a richer type system based on flow analysis. And when I'm talking about flow analysis, I'm talking about the kind of data flow and control flow analysis that typical compilers do to dig really deep into your code, try to understand really what's going on, what it's trying to compute, in order to then try to do amazingly profound things with your code. All right? So we want to bring that kind of flow analysis to the type system. And this type system needs to be carefully designed so that it can enable a blazing fast implementation. So we built Flow. Flow is a new type checker for JavaScript that we have built at Facebook to address programming the large issues without ruining any of its good parts. In this talk, I'll describe some of its more exciting features and what we'll be doing with it in the near future. Note that Flow is already being used by developers at Facebook. We're still working on it. We hope to open source this later this year. All right, so let's dig a little bit into the Flow type system and see how it addresses this tension between static types and expressiveness. So let's start off the very simple example just to set the stage. This is vanilla JavaScript. What we have here is a function that computes the area of a circle given its radius. So obviously it expects a number, and we call it with a string. So what do you think happens here? Do you expect this program to crash at runtime? No. Yeah. This is JavaScript. How can it crash at runtime, right? So yeah, so this is one of the scary bits of JavaScript. What it'll do is convert that string into a number, and then it'll plow on until it probably launches a missile or something. Right? By the way, some of you might be JavaScript ninjas here, and you might think, Well, this code looks harmless enough. You have a 10 in there, basically in disguise. If you convert it to a number, it's just going to be the number 10, so everything is going to be fine. So just to mess with you guys, I changed that 0 to an O in the 10. So what you'll get is the number nan, which is not a number. Okay. So anyway, high-level point is that we listen to our developers at Facebook. They think that this is one of the really bad parts of JavaScript. Implicit conversions, 99 times of 100, lead to hard-to-find bugs that actually prevent them from moving faster rather than enabling them. Right? So they call bullshit on this. We want to catch these errors before the program even runs. All right, so we run flow on this example, and as expected, it gives a type error at the call side saying that you're passing in a string where a number is expected. Okay, so that's good. So is there any surprise there? Well, note what we had to do to run flow. All we did was add a comment header indicating that flow should type check this code. We did not have to change anything else. And flow gleaned all the information that it needed just by looking at the original JavaScript code. It knows that mat.py is a number. It knows that multiplication operates on numbers. By some very simple data flow analysis, it knows that that string argument will eventually find its way to that operator, at which point it will be converted to a number, and that's kind of scary, as we just saw. So it's going to raise this type error. All right. So let's move to a slightly less trivial example. All right. So here we define a function that computes the size of its input by looking up its length property. So if you pass it a string, you're going to be just fine. Again, just to mess with things, we pass it null. Now this falls into an interesting class of JavaScript idioms, those for which traditional static type checking is not precise enough. Now what do I mean by that? Well, of course you'll find code like this in conventional statically typed languages, and it type checks, but it should not. This code is unsafe, and the fact that a type system cannot recognize it as such is kind of a bummer. So when you run flow on this code, we actually trace the path through the code that ends up with a property access on null, and we'll throw a type error here saying the property is not found in null. All right? In other words, flow tracks null, and it considers types to be non-nullable by default, which means that null is not part of every type. Now, Tony Hoare calls the invention of the null reference his billion-dollar mistake, and we agree. So really, we are not just interested in bringing traditional static typing to JavaScript. In fact, we are interested in type checking JavaScript as it is written, and sometimes that means calling out bad code that even traditional static type systems would fail to catch. All right, back to the example. So we have this error. How would we fix it? Well, by adding a null check, of course. Every developer in the world knows how to fix this code. And that's it. That's all you need to do, this code type checks. Now, so flow understands the type refinement implied by the null check and applies that understanding inside the if statement. So it no longer needs to erase this error because it knows that input is non-null inside that if statement. So see what's happening here. This JavaScript code is safe as written, and we want to statically check this code, deliver the good news, without requiring any additional annotations or transformations if it's not necessary. And in this case, it's definitely not necessary. All that is needed is path-dependent analysis, which we have. So before we move on, let's address this issue of type annotations once more. So I've been saying that type annotations are not necessary, but type annotations are not all that bad, especially when you're working with a large code base split across multiple files. In JavaScript, it's customary to use modules to manage these files. So you export what you want to export from a module, and then other modules require your module and use it through the interface that you define. Now, it's super useful to document expectations on such uses. And in Flow, you do that by annotating your exports. So the deal is you annotate your module boundaries, and we infer everything within that module. Of course, you could annotate everything you wanted if that's what excites you, but it's not strictly necessary. In fact, you can actually have Flow help you come up with most of these annotations as well. But I'm digressing. Back to these annotations. So to clarify how annotations work, we have split up our example into these two files. And you can document your expectations by annotating the function size, which you're exporting from the first file, annotate its input by the type nullable string. So the question mark means nullable. And that makes sense because we have just rewritten this function to accept both string and null. We also annotate the return type with number, and Flow checks that along both branches of the if statement that type is valid. And it is. 0 is a number, so is the length of a string. All right. So a combination of sophisticated annotations and path-dependent analysis can be pretty useful. So here we have changed the specification of the size function to take either a string or an array of strings. So there are two cases. If it's a string, we compute its length and return it. Otherwise, we iterate through the array of strings, compute each of those lengths, sum them up, and return the sum, right? So in Flow, you can document your expectations again by using a union type. So the bar there in the type for unit means union. So you can constrain your inputs to these two cases by using a type annotation. And then Flow can use its path-dependent analysis to refine the types of input inside each of these branches. So when under the string check, it knows that input is a string. Otherwise, it knows that input must be an array of string, and therefore this code type checks. Again, you don't have to change how you code in JavaScript. All right, so no JavaScript was harmed in the making of this presentation. So now let's pause for a moment and think about how you might port this function to a language that lacked these capabilities. All right, this is going to be a pretty subtle point. Of course, you could always use downcast, but then you would get potentially unsafe code. So let's say we don't want that. We want to stick to static typing. What will you do? Well, your options are kind of limited. You could use static overloading on this function, but that's not really an option for JavaScript because that would mean that the language runtime has to understand static types. So otherwise, you can use dynamic dispatch. And to do that, you would have to have the type of input be some kind of interface that implements a size method. And then you would have to make the necessary call into the function body, and then you have to fix up all the call sites, wrap them up with instances of classes that implement this size method appropriately. All right, or something else. But really, there's no simple solution to this problem. Unless your type system is designed to work seamlessly with the idioms you love, it forces your programs to look like they were in a different language entirely, which is kind of a bad idea because you end up neither here nor there. All right, so zooming out a little bit, here's one way of looking at the process of typing JavaScript and also understanding what our goals with Flow are. All right, so if on the left we have a JavaScript code base as it exists today, then in the middle is what happens when you try to port this code to a traditional type system. So some of it easily goes through, and that's good. And then you have to port some other code, and this results in some translation and loss of fluidity. You might end up with safe code, but it sure is ugly code. And then you have to cheat for the rest. So basically, you have to use dynamic downcast or something else to get around the type system. So our goal, per the previous examples, is to port JavaScript while minimizing the orange and the red parts. So while minimizing the amount of transformations and by minimizing the amount of potentially unsafe code. All right? So of course, there's a continuum. We continue to push the boundary, but that's where we're at. So let's wind up this overview of the type system by noting something really, really interesting. It turns out that the type system we devised to meet the design constraints we have described here is built on exactly the kind of flow analysis that you would need to build other code intelligence tools on. So if we think about the pyramid of information that supports type checking, knowledge of bindings, references, dependencies, etc., then you can imagine the kind of tools that might make use of this information if it were easily available. Once your machine is able to understand your code base as a graph of linked definitions rather than a bunch of text, it can help you not only find type errors at runtime, but it can also help you in a variety of other things like refactoring or optimizing how parts of your program are loaded for performance. So the possibilities are endless, and we're pretty excited about this. All right, so this is all well and good. We have a really powerful type system. We just now have to make all of this work at scale, right? So remember the other design constraint we had, right? Don't ruin the development experience by putting delays and bureaucracy between coding and running. If you have a huge code base like we do, well, good for you, but not an excuse, right? We can't kill the experience. Otherwise, remember, our developers don't care. They just will use something else. All right, so our solution is simple. We just move all of this type checking to the background. What do I mean by that? Well, we maintain type check results as well as other code intelligence in a persistent server that runs in the background and watches an entire code base. The server updates its model of the world proactively and incrementally. We perform incremental rechecking as files change, and this includes not just file saves, but also includes things like rebasing or switching entire branches. So the increments that I'm talking about can be pretty big, and just keeping up is a challenge, is an engineering challenge. Our tools, be they through the command line or the IDE, simply query this server for results. And these results are delivered back pretty much instantaneously. So this is how we achieve instant feedback. Now, how do we do this? Well, we had to design a type analysis to be completely modular. Remember what we said about modules earlier? Modules come with explicit annotations at module boundaries. All right? And these annotations help us type check individual modules separately, as well as minimize the amount of work that needs to be done when files change. In turn, we can throw powerful flow-based inference and checking at the code inside these modules without worrying about performance. The analysis is implemented using aggressive parallelization and multiprocessing, and this is pretty much a necessity at the scale we work at. If we want to give users the experience we have been promising we should give, not just at the command line, but also, for example, within an IDE. Again, we need to ensure that as far as possible, a request for a type check is simply a query against the current server state so that it can be met with an effectively instant response. Okay, so that's just a brief overview of what flow is. To wrap up, we are going to quickly rip through some other stuff that we support. We support ES6. We actually write some ES6 at Facebook. ES6 is the latest version of JavaScript. That means we support all of these useful and forward-looking features. Classes, which capture a common existing pattern of encoding inheritance using prototypes. Arrows or lambdas, which provide a convenient syntax of functions and also fixes some of their lexical binding properties. Destructuring, which again provides a convenient syntax for doing pattern matching, and also encourages a style of programming where you pass structures by value rather than reference. Optional parameters, default, rest, spread, all of these encourage functions to be more explicit about the kind of arguments they expect. Promises, which are a great way of doing asynchronous programming. And whatever else, as these features roll out, we support them. In fact, we are committed to track JavaScript standards as they evolve. Jeff, who was up here earlier, is one of our representatives at TC39. TC39 is a committee that guides the evolution of JavaScript. So we are contributing to the discussions on where JavaScript is headed. We're also using what we are learning by analyzing JavaScript to provide feedback back to the committee. Another design decision we put a lot of thought into was to remain syntax compatible with TypeScript. Our goal is to fit as smoothly as possible with the current and evolving JavaScript culture. And the TypeScript syntax is reasonable, it has good traction, so we see no reason to mess with it. There's a lot more going on in the type system. There's too much to go into here. But the high-level point is that Flow has a deep understanding of JavaScript's core constructs, what they mean, and how they are combined into common and useful idioms. Just to give you a flavor of what we are up to, consider tuples. Here is where we type small arrays, which are used in a tuple-like form, simply by associating fixed types at their positions. Not just for fun, but because it's a recognizable idiom that actually makes JavaScript development more fluid and safe. Finally, we are fully integrated with React and JSX. These things, which originated at Facebook, are obviously at heavy use inside Facebook, but they're also extremely popular outside, and we are proud to be associated with that project as well. So that's it. As I said earlier, Flow will be open source soon, hopefully by the end of the year. We can't wait to see you guys use Flow in your JavaScript projects and tell us how it helps you move faster. Thanks, and we'll now take questions.
Thanks, Avik. Yeah, Flow is really exciting. We started using it internally a while back, and developers really like it so far, so it's really exciting. Any questions? I'm sure there must be some. No questions?
Yep.
Man, I have a few. Yeah. Is there any way we can try it yet?
We'll contact you if that's possible. We are still working on the details, but right now it's still under development. The plan is to open source it by the end of the year. If we do something in the middle, we'll let you know.
Very soon. Some people are tweeting about it already, so we got to get this guy on Twitter responding.
All right.
Question up here.
Could you tell us more on why you didn't? Oh, thank you. Could you elaborate a little bit on why you didn't fork, maybe TypeScript, or why you didn't pick TypeScript?
There were lots of reasons why we didn't fork TypeScript. At the time when we made this decision, TypeScript certainly did not scale as well as we wanted. The other thing about TypeScript is that it relies very heavily on annotations. If you don't provide annotations, then it's very easy to get around the type system. And what we wanted was more type inference so that we could actually type check programs as they were written. So we tried out various small things. Like there were lots of small cases in TypeScript where it's really, really easy to write unsafe code, but TypeScript just assumes that these constructs have type any, so you can get around the type system pretty quickly. So those were the two basic reasons. Also, we have our own reasons, right? So having something that we are building is extremely useful because we have a lot of DSLs in use inside Facebook as well, and it would be a pain to kind of sync up on those things. But as we have said, we have remained syntax compatible with TypeScript. It actually helps us a lot because we can suck in type annotations for library definitions and so on. And we have a lot of other advantages. We know some of the folks who worked on TypeScript. We are certainly open to collaborating with them in the future and so on.
Question up here.
How does it compare? Well, how does it compare with some of the static analysis that, say, WebStorm would do on your JavaScript?
What kind of static analysis are you talking about? More like code intelligence, refactoring, and so on?
Yeah, WebStorm has a pretty sophisticated component to kind of give you some of these hints that it looks like Flow's doing.
Yeah.
I'm curious where Flow differentiates itself.
I would imagine most of this stuff is something that Flow does and will have to do as well for its IDE. I think these are in slightly different categories. What we want is like very strict type checking. We don't just want hints. So it's kind of easy enough to do hints that work while you're doing programming. You can pretty much easily hook up something like autocomplete and some other things. What we actually want is type checking across module boundaries that is pretty strict. So I can imagine that there will be a lot of overlap between these two analyses. But here what we are trying to do is develop a type system that scales very well, and it does this one thing really, really well. On top of it, we are trying to build some other code intelligence tools, but type checking is our primary motivation.
You mentioned that TypeScript compatible. I'm here.
Yeah.
So that you could pull in a library and not have to necessarily recompute everything. But how would your analysis compare with TypeScript? And have you found instances where you outperformed?
Where we outperform how? In terms of time or?
The like the intention,
precision.
I guess. So if somebody was saying that they wanted some set of types, could Flow look at that and find that, oh, actually this other use case would work well?
Yeah. So what I meant by syntax compatible is that if you type annotate some library in TypeScript and we suck that definition in, we will translate that syntax into our own types. Now we have some subtle differences between the types. I mentioned that we assume that types are non-nullable by default. So we might interpret some of those types as non-nullable and be stricter in some cases. But the real benefit is we can simply take, for example, if these are primitive libraries, most of these type annotations are completely believable. In fact, most of our library definitions actually are copies of TypeScript library definitions. And for those, we can just reuse those type annotations. The power that we have that kind of goes over and beyond TypeScript is that once you suck in those annotations inside your code, as those types flow, we'll do probably a better job of tracking those things. So inside your modules, you will require less annotations just to preserve that information. We will just preserve that information for you.
Other questions?
Are there
Back
any
here.
questions for Jeff? Jeff, do you want to come up as well?
Jeff can come up too.
Yeah, hi. Just a question about the power of your flow tracking. So you gave this example of tracking null values flowing into other functions. Do you track flow of values through stores and subsequent retrieval of properties from objects? And how precisely do you think you can do it?
We have a pretty sophisticated object model as well, which I did not go into at all here. It's mostly heap insensitive though. Because we are in type land, we don't do a lot of context sensitive analysis. We don't really change the type of objects too much. We kind of take the type view that every property has to have a certain type. However, there are some subtleties here. There are some JavaScript idioms that we want to model where objects are initialized as they go, so the object type can actually grow as the code progresses, and at some point it becomes sealed, and we consider that it's fully initialized, and we don't allow it to extend any further. So we have some of that sophistication built in, but mostly the answer is we are heap insensitive.
So another one here on the left somewhere. No? Other questions over here? Okay. She's got you.
You showed an example where you annotated types at a module's interface. So what's the syntax like for that? Do you use comments for it, or are you rolling a JavaScript dialect, like React did with JSX?
Can you point to which example you're talking about? The split.
Yeah.
This one?
Yeah, that one.
The before that one? This one? So these type annotation syntax is all that we are adding to JavaScript. We have some more stuff that we use internally, like JSX, which is a syntax for writing UI, but that extension is orthogonal. Once we take the base language, all we are doing is adding syntax in the form of type annotations. So yeah, mostly TypeScript syntax with some additional operators that we, type operators that we have.
I think you're asking like, how does this actually run? So when we transpile our code, we transpile from ES6, and we actually transpile these out. So they just, they're effectively just comments. They just come out of the code before we deliver it to the JS engine. But yeah, like TypeScript syntax, and then it gets crushed out.
Okay. So it's still valid JavaScript.
Yeah.
Right. Any other questions over here? So we have some iPads again. We're going to pass around. I don't know if you guys have seen this yet. The little button. Press the button. Green is good. Red is you didn't like it. So we'll be passing those around. Any other questions for Vic or Jeff? Any questions about Flow or anything else? Cool. Well, let's thank these guys once again. Thank you so much. I'll plug the Facebook group once again as people are leaving. Both of these guys are in there. I think one of us added them. So if you have more questions about this, if you want to hear more, if you want to be kept up to date, join the @Scale 2014 web group on Facebook. Next up, we're going to have Jafar from Netflix. We'll get him set up here, and we'll get started in a couple of minutes.